The last talk for today's session is by Omid Makhmali, Einstein-Weyl-like condition ruled affine spheres and causal structures in 3D. So please, Omid.
Thank you, Boris. Yeah, I'm going to talk about some generalizations of Einstein-Weyl condition that Boris talked about a little bit. Fortunately, the paper was supposed to be finished by the end of summer, but I was occupied with organizing a workshop, so probably will take some more time to finish it. It was in an archive. So as Boris said in his talk, a Weyl structure on a manifold. Here we're only want to talk about three-dimensional manifolds, and we want to consider only Lorentzian signature. So a Weyl structure is a pair of, this is one way of defining it, a torsion-free affine connection, nabla, and conformal class of a Lorentzian signature on a three-dimensional manifold, such that the connection preserves the conformal class. So the covariant derivative of G is proportional to itself for some one form phi, and this phi goes under this transformation when you change the metric by a conformal factor. So alternatively, one can define Weyl structures in terms of equivalence classes of these pairs G and a one form, and cook up a unique torsion-free affine connection. And then there is these interesting classes of Einstein-Weyl structures, which says that in the Weyl structure, you would like to have a, the condition is that the symmetric part of the Ricci tensor of this affine connection is proportional to a metric in your conformal class. So yeah, people have studied it to some great extent, and Boris again elaborated some interesting facts about these things. It's also quite well known that in this case, there's a one-to-one correspondence with Einstein-Weyl structures and third-order ODEs on their point transformations with two vanishing conditions that are known as Wunschment invariant and Cartan invariant. So if they vanish, you get an Einstein, we get all Einstein-Weyl structures via third-order ODEs. So there is another characterization, sort of in the spirit of Penrose's twistor program, that was, again, Paul Todd attributes it to Cartan and Hitchin, is that the Einstein-Weyl property is equivalent to the existence of a two-parameter family of null surfaces. So these are null surfaces with respect to this Lorentzian conformal structure, and these surfaces are totally geodesic with respect to the projective structure induced by this affine connection. Again, a surface is null if the annihilator of the one form that annihilates the tangent planes is null at each point. And this two-parameter family of null surfaces is that at each point of your manifold, there passes a unique null surface through each point and along each null plane. So these are some sort of integrability. This is similar to, let's say, self-duality, like Penrose characterized, and this is in the case of Einstein-Weyl geometry. So in a certain sense, one can easily imagine that it's very easy to see that through each point of the manifold, exactly one parameter family of null surfaces passes, and then take the tangent plane to those surfaces, and this one parameter family of tangent planes, these null planes, exactly give an envelope construction of the null cone at that point, because we're Lorentzian, so there's a null cone at each point. Again, I'm putting this hat because I want to say that this is a cone as opposed to its projectivization. So let me introduce this notation, is that if I don't put this hat, that means I'm considering the projective null cone at that point. So these are vectors. These are equivalent class of vectors in the projectivized tangent space at point X, which are null with respect to this conformal structure. And the bundle of these basically, so we're in 3 dimensions, so the projectivized tangent space is projective plane. And these guys, because they're this is a quadratic condition, are conics. So you have a bundle of conics over a 3-dimensional manifold, and this is called the sky bundle, or the projectivized null cone bundle. So there's an easy question. What if we have this twistor characterization, and let's deform these conics to something, again, non-degenerate, but not necessarily quadratic, not conic. So these are what I call causal structures. And we want to sort of have this existence condition of this 2-parameter family of null surfaces, see what we end up with. So this causal structures, again, to start to say that there's basically thesis of Jonathan Holland, and they, together with Sparling, they put out a paper showing that very nice geometric construction is that if you start with 3rd-order ODEs under contact transformations, these classes are the same as 3-dimensional causal structures in the sense that I said previously. So you have a 3rd-order ODE, and then you want to sort of take away all this coordinate dependence. So you allow these contact transformations. And they basically, on the solution space of this ODE, which always exists locally, they cooked up a Lagrangian uniquely defined up to scale. And that Lagrangian is not necessarily quadratic, but it's always has this non-degeneracy condition. So it's null cones defined. You have a field of cones arising from the vanishing of this Lagrangian, and they call it a causal structure. You can just forget about any relation with 3rd-order ODEs and try to just solve the equivalence problem for this sort of having a field of null cones. See what you end up with. So you have to consider the sky bundle, so projectivize all your null cones. So you have a 3-dimensional manifold. You have these cones and projectivize them. So you get a projective curves in P2. So this is, you get a 4-dimensional subbundle of the 5-dimensional projectivized tangent bundle of M. Again, we call them sky bundle, using the same terminology as conformal geometry. And then one can show that, so here, let's say at a tangent space, this is your cone, and let's say this ray corresponds to a point in your sky bundle. So this is the ray that corresponds to a projective point upstairs in your sky bundle. And then take the pre-image of this line, and this introduces a 2 distribution on your sky bundle, the pre-image of this line downstairs. And this 2 distribution on this 4-dimensional manifold, first of all, is an angle distribution. So its growth vector is 2, 3, 4. And it's equipped with a splitting. So this V is vertical with respect to this fibration, because you have this natural fibration. And then because it's an angle structure, it has a characteristic line field that I denote by L. So this sort of integral curves of V, as I said, we call them skies. And the integral curves of L, this characteristic line field, is an analog of null geodesics. So if these cones are quadratic, exactly they project to null geodesics on M. So there's again, now that we've solved the equivalence problem for these causal structures, this is, we kind of recover something that has been really studied by many, starting from Chern, who studied contact equivalence of 3rd-order ODEs, and then more thoroughly by Pavel and his PhD student, and then Sparling. And so they studied this aspect, 3rd-order ODEs, and Sparling sort of cooked up the 3-dimensional causal, but one can do it directly and observe that 3-dimensional causals there have, they define a parabolic geometry of this type. So it's B2 and you cross both nodes. And the sky bundle is equipped with an angle structure with a splitting. So immediately you see the connection to 3rd-order ODEs. And there are 2 harmonic invariants. I denote them by I0, which would be the Wunschmann invariant, but now we're viewing it as a causal structure. We don't start from a third order ODE. And something that sort of is a generalization of cotton tensor. So if this is 0, you're in the realm of conformal geometry, and this sort of gives you the cotton tensor. So in terms of, we can also put some coordinates. So we have the sky bundle, and we view it as a graph in projectivized tangent bundle. And so we are taking an affine chart here. So this has 4-dimensional. We take 4 coordinates, x1 to x3 and t. So this t is the sky parameter. And then we see that, for instance, this Wunschmann invariant takes this form. So this is the vanishing of this. This is sort of well known that the vanishing of this shows that these skies are quadratic. And this other invariant has more than 2,300 terms, which is really, ridiculously complicated. But it's funny that in the case of, if you start from, your defining functions and given in terms of third order ODEs, it's just one term, and that's the 4th derivative of your ODE with respect to y double prime. So it really shows how, changing set of coordinates can simplify expressions, and so this was interesting. So we call it causal structure. Now we want to, again, as I said, we want to sort of see how far we can push the definition of Einstein-Weyl. So we define a causal structure to be augmented if it is equipped with a 2-parameter family of null surfaces. But null here is now with respect to this causal structure. So we sort of define it alternatively as this sky bundle is foliated by surfaces that are transversal to the sky. And then when you push them down to the manifold, they sort of lie in this affine tangent space to the cone. So they sort of, their tangent plane, when you push them down, lie on this affine tangent plane to the cone at each point. So this is like, they're null in this way. Then you can see that in this augmented causal structures, the derived system of your 2 distribution has a splitting. So there's the V, the vertical tangent vector, and then there is a 2 distribution that is integrable. So its integral leaves give you exactly these null surfaces that foliate the sky bundle. And once you have this splitting, immediately you get a 3-dimensional reduction of the structure bundle. And then you recover this theorem that I'll explain how this is sort of basically what Cartan said in studies of Einstein-Weyl geometry, and sort of more explicitly and thoroughly investigated by Pavel. You get that 3-dimensional augmented causal structures, again, define a Cartan geometry. This one, the structure bundle is 7-dimensional because you've reduced 10-dimensional original bundle by 3 of this type. So it's semi-direct product geometry. And there are now the fundamental invariants. You have 4 of them, which includes also the Wunschmann. And this is called Cartan, and there are 2 more. So the reason that I said this is basically what Cartan had is that because you can show immediately that augmented causal structures are in 1-to-1 correspondent with now point equivalence classes of third order ODEs. And this is easy to see because you see, we have a 2-parameter family of surfaces which you can view as level surfaces of 1-parameter family of foliations. So fix T and then change U, you get these level surfaces, you get a foliation. And then by changing T, you get a 1-parameter family of foliation, which gives you these 2-parameter family of surfaces that we assume to be null. And then once you have this, by consecutive differentiation, you can eliminate x1 and x3 and end up with a third order ODE. So you can, this is basically because everything is similar to the point equivalence class of third order ODE, the equivalence problem we solved previously is basically what Cartan had, but we're just viewing it from another from another direction, starting from a solution space. Now there's one more thing in Einstein-Weyl geometry that, remember, we had this affine connection that we're not seeing any trace of it so far. But we see that actually in this case, for all these augmented geometries, augmented causal structures, we have a three-dimensional path geometry on M. So to define this, we should sort of define path geometry more abstractly as a geometry that is modeled on, a three-dimensional manifold and a projective tangent bundle. And we want a foliation of this projectivized tangent bundle. And the curves sort of, we want them to be transversal to the fibers. So this is path geometry abstractly. And then if you look at what you have in for augmented causal structures, you can see that if you take your structure bundle, the 7-dimensional that we obtained from reducing the 10-dimensional structure bundle by 3 parameters, and mod it out by the center. So remember that this is our Cartan geometries of this type, right? So we are basically, the homogeneous model is this semi-direct product mod out by the upper triangular matrices of CO21. And take the center of CO21, okay, it's 2-dimensional. And then when you mod them out, you end up with a 5-dimensional manifold. And this fiberation of sigma over M3 exactly gives you a path geometry. So path geometry, basically, if you push down, you have locally, this is very local, even micro local, that you can find at each point of M paths along each direction, right? That's why we call it. So if these paths arise from a connection, affine connection, it's a projective structure. So now we are having path geometries, do not arise necessarily from a connection. And in the study of path geometries, again, there are these fundamental invariants. There's a torsion. It's a parabolic geometry. There's a torsion, which defines a binary quadratic, and a curvature that defines that is given in terms of a binary quartic. And this is the first sort of non-trivial observation, is that for these path geometries arising from augmented causal structures, this quartic has a root of multiplicity at least 3. So this was, and then if the Wunschment and the Cartan invariant vanish, then this path geometry is projective, and you basically get exactly what you had in the Einstein-Weyl geometry. And another thing is that these surfaces that we sort of augmented our causal structure with are totally geodesic for this path geometry, meaning that the path, if one of them starts along a direction on these surfaces, it remains on this null surface. It doesn't leave it. So they're sort of totally geodesic with respect to this path geometry. And the path, now you have path geometry on each of these null surfaces. And in fact, it's a projective structure. So it defines a projective structure on each of these null surfaces. So this is really similar to, in some sense, the twistorial characterization of Einstein-Weyl structure. And in a sense, it's a little bit even tautological. So there's not much that we have done except this multiplicity, but there's, we can see that everything goes through, but conformal is now causal, and projective structure is just path geometry. Now we want to look at this a little bit more carefully, and we see that, let's just first start by defining what a Finsler structure is. So again, the same way we define causal in terms of conformal structure, we define Finsler as a sort of a curved version of, or pseudo-Finsler, a pseudo-Riemannian geometry. So in pseudo-Riemannian geometry, you have, let's say, your unit sphere, or your hyperboloid, your set of space-like vectors, or time-like vectors, or unit vectors. And then this is always a sphere, a quadratic, an affine quadratic. And you would, in Finsler geometry, what they do is that you just drop this quadratic condition and make it an affine hypersurface. So you don't require that it comes, it's quadratic. You just drop this quadratic condition and let it be a non-degenerate affine hypersurface in each tangent space with, again, a non-degeneracy condition. And in this case, I'm interested to, again, this affine, so in our case, we would like to have this, so in 3-dimensional Lorentzian, we have this because it's Lorentzian, we have space-like vectors and time-like vectors. And we have a set of one-sheeted hyperboloid or two-sheeted hyperboloid. So we want to actually curve up this one-sheeted hyperboloid, the set of space-like, unit space-like vectors. So again, we don't want to do it in terms of writing a Finserian norm and doing it cool. We want to do it abstractly. So abstractly, a Finzer structure, again, can be defined the same way we abstractly define a path geometry. We can abstractly define a Finzer geometry or pseudo-Finzer geometry by looking at the structure on this unit tangent bundle of a Riemannian. We just curve it up. And it turns out that you can describe it this way as a contact manifold. So this is now you want sigma to be a contact with a distinguished contact form that it's referred to as the Hilbert form. And you want it to be equipped with a Legendrian foliation. Each leaf of this foliation would be the fibers of sigma over m. And we want all these leaves, these Legendrian leaves, to be equipped with a bilinear form. Now, in this case, because they are space-like, we want this bilinear form to be indefinite, right? So you have a surface being your Legendrian leaf, and you have a bilinear form of signature 1, 1 on each of them. So it was in 90s, these two Japanese sort of defined a notion of Finsler-Weyl structure. And I define it sort of a bit abstractly by having a sort of these contact forms arising from Finzer geometry, pseudo-Finzer, better to say, and then a connection on sigma that arises from a path geometry. So when a path geometry, but then you take a Weyl connection of a path geometry on sigma, and then you want this Weyl structure to preserve the conformal class of this alpha. So you allow your contact forms to be multiplied conformal, to change conformally. You basically can allow your unit spheres or space of unit space-like vectors to sort of from point to point to be scaled. And you want this Weyl connection of this path geometry to preserve this conformal class. So this is, again, very similar to Weyl geometry I defined in the first slide. And then you can solve the equivalence problem for these Finsler-Weyl structures. I couldn't find any reference for this. So if anyone has solved really the equivalence, but it's not so difficult in general in any dimension. You can, now here we're in just 5-dimension over a 3-dimensional manifold, that it's again a Cartan geometry of this type. As I said, we're considering pseudo-Finsler-Weyl structure, so analog of Lorentzian Weyl structures.
Excuse me, Omid.
Yeah.
So what is the distinguished contact form?
Oh, this would be exactly when you have maybe a best way to say it is that you consider your set of unit vectors, okay? So in the cotangent bundle, and then restrict the canonical contact form to this set of unit covectors, and then sort of by Legendre transformation, go to the tangent bundle, and then you get a distinguished contact form in the case of pseudo-Riemannian geometry. That's one way of doing it. You can write it explicitly in terms of metrics. This is basically how the metric, I could have written it here explicitly, but yeah.
Okay.
So there are 3 invariants for these geometries. One of them is a cubic, symmetric cubic, a bilinear form, and a 2-form. So this is known as the flat curvature. This is sort of arises because we have a Weyl nature of the geometry, and this one is the central affine invariant of each of these affine hypersurfaces that we have assigned to each tangent space. So these are affine, they're not necessarily quadratic. And in the study of, so there's at each tangent space of the manifold, there's a well notion of origin. right? So we have an affine hypersurface, so fixed origin, and immediately this cubic form shows up. That's sort of the central affine invariant. So central affine geometry of hypersurfaces is the study of equivalence of hypersurfaces up to the action of GLN, let's say in Rn plus one, in Rn. And then you, when you study that, the fundamental invariant shows up as a cubic form. If this cubic form is 0, all your these hypersurfaces are quadratic. So you're in the realm of, again, Lorentzian or pseudo-Riemannian geometry. So your Finsler-Weyl structure exactly descends to a Weyl structure. Now, there are other things. You had this bilinear form, and you can basically contract this cubic form by itself, and we're assuming this is indefinite. And if this is equal to 0, then these surfaces, now in this case, because the fibers are surfaces, we're assuming, the surface is ruled. So each of these affine surfaces are ruled, indefinite. And then there's another one that if you just consider this contraction and it's equal to 0, this is known as the Chebyshev form. And if this is 0, these are known as proper affine spheres. So proper affine spheres, they're so affine geometry is the study of hypersurfaces up to the action of SLN and translation. And then when you are studying them, at each point of the affine hypersurface, you have you cook up a frame. So you have your tangent vectors and there's a normal. And when you're studying the affine theory of hypersurfaces, there's a well-defined notion of a normal vector at each point of your hypersurface. And if these normals, when you do this, cook up this moving frame on each point of your hypersurface, if these normal vectors, all of them intersect at one point when you continue them, these are called affine spheres, right? And if they, let's say, are parallel to each other, they're called improper. If they exactly intersect at one point, they're called proper affine spheres. In this case, because we have an origin, here these are, if this is 0, these are affine spheres, and their center, which is these normals, exactly intersect at the origin of each tangent space. And in fact, these are very well known. These ruled, the ruled affine, proper affine sphere, they're exactly parametrized this way for function AX satisfying this condition. This is in book of Nomitsu and Sasaki. So we call the Finsler-Weyl structure integrable if these fibers, these unit space-like vectors, they are ruled surfaces. And moreover, this bundle, sigma, is equipped with a 2-parameter family of 3-dimensional manifolds, like N, which are null with respect to a degenerate. So when you do this, this is, I'm not going to get into the details, but when you're studying these Finsler-Weyl structures, because you have these affine hypersurfaces, you have at each point, you have the osculating quadric to these affine hypersurfaces. And these osculating quadrics define you a bilinear form that is degenerate on sigma. Okay? It has rank 3. It's not a non-degenerate, it's degenerate along the vertical tangent vectors. So you want it to be null with respect to this non-degenerate bilinear form and project to a surface downstairs on M, such that when you look at upstairs, its intersection with each of these fibers is a ruling line because you're working with a ruled surface. It's a little bit, I don't know, maybe overcomplicated definition, but that's I couldn't really try to make it simpler. But what we can show is that this is quite different from the sort of twistor characterization of Einstein-Weyl structures I gave initially. It's a little bit different. And it turns out that these integrable Finsler-Weyl structures, for which these unit space-like vectors, set of unit space-like vectors are ruled affine spheres, they correspond to third-order ODEs now with vanishing Cartan in there. So this hasn't been really this is some nice sort of characterization that is first of all interesting, and it shows that one can show that these are the generalities for functions of three variables. And it's very different from I don't know. So in the case when Wunschmann vanishes, then basically these hypersurfaces, these sigma x's, they're all one-sheeted paraboloid, and you're basically working in the Lorentzian geometry. You're just pulling back everything to the bundle of unit space-like vectors. So it's kind of too much, too unnecessary to do it in the case of Lorentzian conformal structure. Okay, so now we want to extend, again, this is, it's okay, but it's not that interesting because we want to get something that's more rigid, maybe a little bit. So we saw that this, if the Cartan invariant vanishes, then you get these integrable, these Finsler-Weyl structures. And again, we talked about the path geometry defined by a third order ODE previously with a torsion and a curvature. So this was a binary quadric, this was a binary quartic. And then, as I said before, in Finsler geometry, we always have this degenerate quadratic form that arises from the osculating quadric of each of these fibers, your sigma x, sometimes referred to as indicatrice. Now, a natural way of extending Einstein-Weyl condition is that, remember in Einstein-Weyl, you had the symmetric Ricci being proportional to a metric. Here, I have two binary quadrics that are degenerate, and then they're of the same type. They live sort of in the same bundle. I'm not writing it in because it's really not necessary. But a natural way would be that you want the conformal class of them to be the same. So it turns out that if you require this condition, I call them Finsler-Einstein-Weyl condition, then if you consider all the consequences of this, you either get Einstein-Weyl condition, which means that additional to this in the vanishing of Cartan, you have also your Wunschmann condition vanishes. Or you get Finsler-Weyl structures, which are closed, meaning that Weyl form is a closed one form. And they have constant flat curvature as Finsler structures. So you can, let's say, they're defined up to a homothency because this is closed, and you can set the flat curvature to be 1, for instance, or -1, or maybe they're 0. And they have their torsion of their path geometry 0. And this sort of the interesting thing is that now you can go to, you have this path geometry associated to them. If you go to the 4-dimensional space of paths for this Finsler Einstein-Weyl metrics, these proper ones, not this one. So this is all known. And for this one, if you go to the 4-dimensional space of paths, let's say you normalized your flat curvature to 1, -1, or 0, then this space of paths of this path geometry we talked about before, it has a half flat. So this epsilon Kähler metric. So epsilon, if this is -1, this is a usual Kähler with an almost complex structure. If this is 1, this is para-Kähler. If this is 0, it is known as null Kähler. So this, these metrics, they have a Weyl structure, a Weyl curvature that defines coming from this quartic we talked before, this quartic exactly. And these, as I said, this have type 3. This has at least a root of multiplicity 3. And moreover, its Ricci curvature, it's not Einstein, but its Ricci curvature defines another Kähler metric, epsilon Kähler metric, which in this case is Einstein. So I haven't seen this sort of type of metrics before, that you have always, when you have a Kähler structure, its Ricci tensor defines another Kähler structure with respect to the same complex, almost complex structure. But in this case, this new Kähler structure defined by this Ricci tensor is a Kähler Einstein. And the generality of this depends on 3 functions of 2 variables. So Einstein-Weyl is 4 functions of 2 variables, and these guys 3 functions of 2 variables. And in fact, we have the converse. So here I'm putting epsilon equal to 1. So I'm only now I want to discuss Kähler structures. So you start with a self-dual para-Kähler structure, and sort of you can reduce the coframe bundle. So these are the structures group for these para-Kähler structures, are GL2. So there is if the Ricci curvature is non-degenerate, and in fact positive determinant, you can, we require that there's a coframe reduction from GL2 to the center of GL2, such that the Ricci can be put in this way, because this is a self-dual. This has to be, can be put this way, but up to a scale, and I require that that sort of function that appears is 1. So this is an invariant condition for a para-Kähler metric. And this is obviously, because it's of this form, it cannot be Einstein. But also I require that the kernel of this, let's say, para-holomorphic surface is principal for the Weyl curvature of this para-Kähler metric. So there's a Weyl curvature defined by a quartic, and I require that this is a principal null plane of multiplicity 3. Then one can show that this Ricci, this Ricci, in fact defines a para-Kähler Einstein metric whose Weyl curvature is of type 2. So it's a little bit, seems complicated, but I don't think it is. It just, I was surprised that it hasn't been studied. And all such para-Kähler metrics exactly arise as proper integrable Finsler-Einstein-Weyl structures of cos and negative flat curvature that I explained before. So again, you can see what are the, so looking at these structures as ODEs, you can see what gives rise to these, to such structures. They're exactly sort of the sufficient conditions or vanish of 3 nonlinear PDEs. So this is the Cartan invariant. So this is your ODE, right? Y double prime is equal to f of x, y, y prime, and y double prime, where q is y double prime, p is y prime. So this is the vanishing of Cartan. And another condition that shows up if you're in this setting is that the third derivative of f with respect to y double prime has to be 0. And then another sort of a little bit more complicated PDE. And if you give it to Maple, it will exactly generate, explicit solution for f. For one of them, this sort of flat curvature is 0. And for another solution, there are 2 solutions produces, is non-zero. You can normalize it to 1 or negative. So this seems that this is explicitly solvable. And so it's just too complicated to write this explicit ansatz for this ODE. But this, again, suggests that this sort of structure equations, if you start from the structure equations, you might be able to solve it explicitly, integrate it, and come up with some more canonical coordinates. So just one thing that I'll take at least from this is to do the same thing for 4-dimensional causal structures. We dealt with 3-dimensional and 4-dimensional, meaning that, again, I require that the null combs, in this case, be indefinite on a 4-dimensional manifold. So you have your sky bundle, and the sky at each point, I would like it to be indefinite projective surfaces. And when sort of the relation to Finsler-Weyl structures, and then sort of cooking up a notion of Cartan invariant we have for 3rd-order ODEs, but in this case for pair of 2nd-order PDEs, that all these 4-dimensional causal structures that arrive, you can show they arise from a pair of 2nd-order PDEs that are sort of related to what Boris Dubrov was talking about. So he was talking about the linearization of a pair of 2nd-order PDEs, but here they can be completely non-linear. And another direction is just these classes of Kähler metrics were quite interesting. So metrics for which the Ricci tensor of the Kähler, so if Ricci tensor is non-degenerate, it always defines another Kähler metric. And what sort of more interesting class of Kähler metrics whose Ricci tensor defines an Kähler Einstein metric. This is, again, I don't know if this has been studied. Yeah, thank you for your attention.
Thank you. So questions, please.
Hi. Thank you. That was a lovely talk. The so these all have twistor spaces that the integrable two planes form a kind of two-dimensional twistor space, I guess. So do you know of any integral geometry you can do from there? You can imagine that each point in that in your Einstein-Weyl space would give you a curve in the mini twistor space, and you could integrate a function over that curve, and maybe it solves some equation in the Einstein-Weyl space or something. Have you thought about that at all?
Yes, I know. I think that's one of the sort of directions I haven't thought about it, but I mean, obviously you have it from what Hitchin did. He exactly considered this sort of going to the plane, and you have these rational curves with normal bundle O2, and then he related it to this Einstein-Weyl. But I don't know, in this case, it's a little bit more complicated.
I can see the geometry is very complicated and so on. I mean, there's no longer a Penrose transform because these curves are not compact or anything, but you can still imagine some interesting integral geometry, perhaps. But
yes, I hope something can be found. Something.
Other questions?
Could you remind me of when you were talking about the path geometry, the 5D path geometry? So you have your torsion, your curvature, and one of them is a quartic, and then you had some condition that for which you got algebraic speciality, like at least multiplicity of root multiplicity of at least 3. Can you just remind me of what the condition was that established that?
So that was just an organic part of, I mean, path geometries that arise from augmented causal structures, they have multiplicity 3, their curvature. And I don't know why. I thought, actually, that was the first surprising thing that.
Yeah. That's quite constrained. I mean, just curious, have you constructed some homogeneous path geometries with precisely multiplicity root 3? And I'm just asking this because, I mean, in 235, there are no homogeneous models with Cartan quartic multiplicity 3. So I'm just wondering, in your context, have you encountered?
I know I haven't, but that's actually when I came across this multiplicity theory, I exactly thought about, if there's, but yes, you're right. But I haven't done it, but I know that how multiplicity having type 3 is sort of even so. There was this work we did with Pavel on para-Kähler Einstein, and we wanted to give examples for each algebraic type, and the most difficult case to sort of integrate and give examples were exactly when the algebraic type was 3. And but I haven't really gone down to considering homogeneous models. No.
But you haven't ruled out the existence of constant root type 3.
Mm.
Did I understand correctly?
Yeah, but I don't know if there exists a homogeneous model of type 3. I don't know if that's what you're asking, because I didn't hear you.
You have some non-homogeneous examples with the root type 3?
Yeah, I think yes, there are non-homogeneous. Yes,
there are non-homogeneous. Okay.
There are, yes.
Can I also ask you? Is there anything special if you consider, for example, cubic causality?
Consider what?
That your causal structure is cubic, not quadratic, but cubic.
I don't know, because we considered this with dimension 4 with Wojtek to consider when the null cones are cubic in this actually Kähler ruled cubic, and try to see how we can. But yeah, it wasn't. We didn't get. We got many of the aspects of, let's say, half-flat conformal geometry, but it just became, we didn't get, the system got too overdetermined. That was sort of unsatisfactory. But in this case, I don't know. I haven't examined. Maybe it will be. I think it's just a little bit, it makes it too rigid if you require all these guys to be, let's say, of type Q of cubic. I think it just makes it too, I don't know.
And you don't know, for example, how it would reduce functional counting, right?
No. We were unable to count.
Other questions? Okay. Thanks very much.